we have looked at how intermolecular forces interact to predict solubility. We mainly focused on solids and liquids, but gases can also form solutions with liquids. When we talk about an ideal gas, we know that by definition there are no intermolecular forces between the gas particles. Thus, the delta H of that part of the solution formation energy curve is zero. This means that gases will mix with liquids in an exothermic way, since no energy is released in the first step. Thus, gases are less soluble with increased temperature. We will look more closely at this energy process later on, when we talk about equilibriums and free energy. But for now, you should remember that the formation of solutions between gases and liquids is exothermic. Work through pages 36 and 37 in the workbook. There are a few solution properties that depend only upon the total concentration of solute species, regardless of their identities. These are called colligative properties, and they include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. In order to consider the applications and mechanisms of these properties, it is important to understand the different ways that we can express the concentration of a solute. We have seen molarity before. Molarity is simply the moles of solute per liter of solvent. This makes sense in situations where a gas or solid is dissolved into a liquid. However, what happens to water when you cool it down? The solution contracts. This means that the molarity will change slightly because there are less liters, even though the same number of moles of solute and solvent are present. We can get around this by using different methods of considering concentrations. One method should be also familiar to us. This is referred to as a mole fraction. A component's mole fraction is equal to the moles of that component over the total moles of the solution. We used this in gas law equations before, but it doesn't have to just be restricted to gases. Let's add another concentration unit that is completely new. This is referred to as molality. Molality is defined as the moles of solute per kilogram of solvent. Since molality only depends on masses and moles, it's temperature independent and is suited to applications, like several colligative properties that we will discuss later. We can also talk about concentration in terms of mass percent. This is defined as the mass of a solution's component divided by the total mass of the solution, times 100. In the same way, parts per million is the same calculation, only times a million instead of 100. Let's look at a solution and calculate all of our concentration values for it. Let's say we have 30 grams of glucose in 100 milliliters of water with a density of 1.27 grams per milliliter. The mass percent of glucose in this sample requires us to calculate the total mass in grams of the sample, which we can do using the density. So the mass percent is equal to 30 grams of glucose divided by 100 milliliters times the density of 1.27 grams per milliliter, all times 100, which gives us 23.6% glucose. For parts per million, we do the same calculation, but multiply by a million. We get 236,000 parts per million. Molarity is something we've done a lot, so we won't go over the details. The molar mass of glucose is 180.15, and we get 1.67 molar glucose. For molality, we need the moles of glucose in the kilograms of water. We have the moles of glucose from the molarity calculation, so we can use the density to calculate the total mass of the solution as we did before. Then we can subtract out the mass of glucose to get only the mass of water. Then we convert the mass to kilograms and divide. This gives us 1.72 molal of glucose. Molality is symbolized by a lowercase italic m, but can also be written as molal to avoid confusion with meters. Now that we have moles, we can calculate the mole fraction by dividing the moles of glucose by the total moles. Remember that we need to use the mass of water and the mass of glucose to find the total moles of each. We get 0.0301. Make sure you review this and molarity if you are having trouble with these concepts. Review and work through pages 38 through 41 in your workbook. Now that we have a toolbox of concentration measurements, we can look at 4 important colligative properties. These are properties that only depend on the solute and solvent concentrations and do not depend on their chemical structures. These are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Let's start with vapor pressure and how the vapor pressure of a solvent is affected by the introduction of a solute. Vapor pressure is the result of a small number of molecules from the surface of a liquid gaining enough energy to jump into the gas phase. The higher the temperature, the more molecules will cross this energy threshold. In a sealed container, the collisions of these gas particles with the walls of that container create vapor pressure. It's important to understand that these molecules are coming from the top layer of molecules in the liquid at any temperature, significantly below the boiling point. A substance that has no vapor pressure is considered non-volatile, while a substance that has a measurable vapor pressure is considered volatile. When a solution is formed by dissolving a non-volatile solute in a volatile solvent, the vapor pressure of the volatile solvent is reduced. This is because the non-volatile solute helps stabilize the volatile solvent in the liquid phase. One way to view this is because the non-volatile solute occupies the same amount of space at the surface, and this reduces the surface area available for the volatile solvent to occupy and vaporize. Thus, less molecules or solvent are available to be pushed into the gas phase, and the vapor pressure is consequently reduced. Mathematically, this is represented using Raoult's law. This law is basically just a partial pressure equation, similar to what we saw in the chapter on gas law. The partial pressure of the volatile solvent is equal to its vapor pressure times its mole fraction. Let's give this a try. A solution is made by dissolving 280 grams of glucose into 200 milliliters of water. We're assuming that the density of water is 1 gram per milliliter, at 25 degrees Celsius. The vapor pressure of pure water at this temperature is 23.76 torr. What will the vapor pressure of the solution be? We need the moles of H2O in glucose. For glucose, we can calculate this directly using the molar mass of glucose. For water, we need to use the density and convert to grams from milliliters, and then use those grams to calculate the moles of H2O. We then calculate the mole fraction of water as we did in the past for partial pressure of gases. Then, we can multiply the mole fraction of water times the vapor pressure of pure water and get our answer, 20.8 torr. This is a reduction of 2.9 torr. Let's consider what happens to the vapor pressure when we mix 2 volatile substances together into a solution. When we have a mix of 2 gases, and we want to know the contribution of total pressure by each gas, we can use the mole fraction of each gas times the partial pressure of that gas to get the pressure contribution of that gas. If we add up all the partial pressures, we get the total pressure of all gases. This also works for vapor pressure. In fact, if we consider that a non-volatile solute has a vapor pressure of 0, this is the same thing we did for the mixture of a volatile and non-volatile solution. At 25 degrees Celsius, the vapor pressures of benzene and toluene are 93.4 and 26.9 torr respectively. A solution made by mixing 60 grams of benzene and 40 grams of toluene is prepared. What is the vapor pressure of the solution? We need the mole fraction of each component, so we can calculate those using the molar masses. Then, we can get the mole fraction using the total moles. Now we just multiply each mole fraction by the vapor pressure of that pure substance, add those together, and we get 69.4 torr as the vapor pressure of the combined solution. Review and work through pages 43 through 46 in your workbook. When we add a solute to a solvent, there is a shift in the phase diagram. We know that solutes reduce vapor pressure. They also increase the amount of energy required for a solution to boil when compared to the pure solvent. Think about this idea for a minute and see if you can describe to yourself how these are related. Next, we see that the temperature at which the solution freezes will be lower than the pure solvent. Why do you think this is? Freezing is the process of lowering the energy of a substance until all the intermolecular bonds are formed and not interrupted. If we introduce another substance, this will increase the disorder of the system and prevent all possible bonds from forming until more energy has been taken away from the system. We will come back to this idea later when we talk about free energy and its connection to enthalpy. Mathematically, we can represent these changes in boiling and freezing temperatures with the equations. The change in the freezing temperature is equal to the freezing point depression constant times the molality of the solution, and the changing in boiling point temperature is equal to the boiling elevation constant times the molality of the solution. Remember, the molality is moles of solute per kilogram of solvent. Go ahead and try the problems on pages 48 and 49 in your workbook. The last colligative property that we are going to consider is osmotic pressure. Osmosis is a process where solutions are allowed to diffuse through a semi-permeable membrane. Semi-permeable means that some substances are allowed to pass through while others are not. Imagine a U-shaped tube with a semi-permeable membrane dividing the two halves of the tube, like this. This membrane is designed to allow solvent molecules to pass through, but solute molecules are blocked. If we fill the tube with solvent on both sides in a constant pressure situation, the solvent will equilibrate equally on both sides, like this. Solvent molecules are free to move from one side to the other, but they do so at equal rates, so the levels don't change. However, adding a solute to one side that cannot pass through the membrane will cause the solvent to diffuse more rapidly into that side of the tube than it diffuses out of it. This is similar to vapor pressure. If you add a solute, it stabilizes the solution and reduces the vapor pressure. Here, it works in a similar way to reduce the amount of diffusion. This causes solvent to build up on the solute side as it is diffusing in faster than is diffusing out. This continues until the pressure of the increased solution mass is equal to the diffusion force. At this pressure, the solvent is forced back into the other side at the same rate as it is diffusing in. This stabilizes the system at a new equilibrium. The pressure required to balance this diffusion is called osmotic pressure and can be mathematically represented as the osmotic pressure equals the solute molarity times the gas constant times the absolute temperature in Kelvin. The system described here applies to an ideal solution where intermolecular forces don't play a role in what is happening. Let's do a calculation involving osmotic pressure. In this equation, the gas constant must have units of liters atmosphere per mole Kelvin. This is our familiar friend, 0.08206. Assuming ideal solution behavior, what is the osmotic pressure in atmospheres of a 0.30 molar solution of glucose in water that is used for intravenous infusions at a body temperature of 37 degrees Celsius? The osmotic pressure is equal to the molarity of the solution, which is 0.30 molar glucose, and the temperature is 37 degrees Celsius, which needs to be converted to Kelvin. So 310 Kelvin. The units cancel and give us 7.6 atmospheres of osmotic pressure. So far, we've looked at colligative properties, intermolecular forces, and solution formation. These are more detailed explanations of what we looked at in previous classes. Next, we're going to dive into another topic that expands on what we know about chemical reactions. That topic is chemical kinetics, which deals with the speed of chemical reactions.